Alright, hell yeah. So, material mechanics, and we have my first moment video. And so, basically what we're going to be doing is kind of analyzing the cantilever. And, because hell, I can make this, you know what I mean? The type of steel that I, typically build with, at the steel yard would be 2-inch tubing, and it would have a thickness pretty thin, like definitely not 1/8 inch thick. That's hella thick. So my thickness that I preferred, and it was the thinnest you could get for a 2-inch by 2-inch, and this would go 20 feet long. You know what I mean? 240 inches. So the thickness would be 0.083. You know what I mean? And so half inch is 0.5. Quarter inch is 0.25, eighth of an inch is 0.125, and a 1/16 of an inch is 0.0625. So this is right in between an eighth of an inch, and so this would be and a 1/16 of an inch. So it would be, if this was an eighth, that means this is 2/16. How the hell? I kind of forget. Maybe that's is it? Well, this is a 1/16, and if we added another 1/16, we'd get to there. So you have to like take this to, this is 2/32. There you go. This is 4/32. So yeah, we would have 3/32. That's what I was getting at. It's good to do your fractions. But anyway, so what we want to do is put my body weight on it. So we're going to do like 160 pounds, and this is real world. You know what I mean? So and what we're going to do is we're going to figure out the shear forces in this, and because yeah, I mean that's the whole name of the game. We want the shear, moment, what the hell's going on there. And the cool thing about, the take-home point's going to be right now. I mean, I think this is just the best way to do a free body diagram. I kind of came up with it myself, and it's just cool because basically a free body diagram says you can cut anything out of outer space. So just go ahead and dot it out. You know what I mean? And then when you put it down here, it's no longer touching the wall. You know what I mean? So we're just going to do the whole thing. It's just the metal. So if I went to the steel yard and got a 20-foot length, and so this was 240 inches, now I'm just having the metal just floating in outer space. Okay, so that's what the free body diagram is. So we go back to what's actually happening. Well, we observe, visually, that I can stand on this and nothing happens, let's say. You know what I mean? There's no movement. So when we go to Newton's equation of mass times acceleration, you know what I mean? We do have a mass, but we witness no movement. So the acceleration is 0. But we do identify a force. So F equals ma is kind of cool because, you know what I mean, you're looking for changes in velocity, you're looking for motion, but then you're also over here looking to identify what things cause force on this mass. And we know that, hell yeah, we're still, the Earth is underneath us, so when I stand on this, it's going to apply a 160 pound force on there. Okay, so then when we chop it out of outer space, we just mentally just pretend the Earth doesn't exist. All the stars, you're so far into the deepest parts of the galaxy that it's just space. You know what I mean? There's nothing else influencing it. So then, but we still put that what we know about it. We still have a 160 pound force. And what we know about an object that's three-dimensional is that if we have a force on this mass, then it's going to be traveling in this direction. You know what I mean? F equals ma. We should be seeing acceleration in that direction. We don't, and going back to here, because we don't, we need another force that's balanced up here. But there's space, so we go back to our observation. Hey, there's just open space underneath there. That would be a great place to support this. You know what I mean? Go throw like a stud underneath this, and then that could take that 160 pounds. But we do not have that. The only place that can take that 160 pounds is over here, right there. So So booyah. So that's what can take that 160. So now we have 160 pounds right here. Okay, but here's the next aspect of the free body diagram. We now have two forces, 160 pounds over there and over there. And because we have a three-dimensional shape, if we put these forces this way, this whole thing is going to rotate. It's just going to spin. You know what I mean? Wouldn't that make sense? If this thing was in outer space and you put a force that way and a force that way, little rockets, you know what I mean? Just kind of little blowing, rockets. This thing is just going to be spinning and going faster and faster and faster as long as a 160-pound force is kept. But we do not observe that. We observe zero rotation. And so this is the whole idea that these two forces provide a torque. So we get out our right hand and we do the right hand rule. Alright, right hand rule says, hell yeah. This force, kind of goes that way with the fingers, and then my thumb is down. And then over here, same thing. I'm sweeping this way with the fingers, thumb is down. So this is going to be a downward I'm sorry, not downward, but it's just for sign convention, this is negative. This is a clockwise. So we say any clockwise rotation or torque, that is going to be a negative torque. So now we have to balance it this way. And because I guess this kind of gets a little complex. There's nothing going on over here. There's just space too. So when we chop this, when we chop the free body diagram out, hey, we chopped it against something that was going on between this wall and the segment. Well, that's the only place where we can put that moment. So if we have this, and the moment's going to be like 160 pounds times 240, and that's going to be negative. And then so over here we need a positive moment. Did I do that right? I did not do that right. So this is a positive moment, I guess. You know what I mean? Just because with that right hand rule. And that's going to balance that. So this moment is going to equal 160 pounds times that 240 inches. So now we have a moment of pound inches. Okay, so hell yeah. So I wish it wasn't so messy, but now we can cut it anywhere. So let's redo this again, and just if we had to do it in 2 seconds, 160 down. We're going to chop it from the wall. And then so we're still going to have this 160 forces in the Y. We're going to have 160 over here. And then this is going to cause a downward moment, so we need an upward moment. And there you go. So there's our moment. Okay. And let's just say that moment's hella. And now what we can do is we can chop this into as many pieces as we want. So let's chop it right here. And we're going to chop this out of outer space. You can just keep chopping things as much as you want. So let's do that. So we're going to take that. So what do we know about over here? So we know that we have 160 up. We know that we have a moment equal hella. And then forces in the Y. Again, we have this just floating in outer space. We observe a 160 pound force up. We have to have it balanced with the 160 pound force down. And because we've already identified that this was, once we chopped it out of space, we balanced it. And but now when we chop it again, this wall already doesn't exist from this one. And now there's just space over here. So the second we chop it, now internally, so that's where you get that. And so, I mean, the actual thing to do with the textbook is if you have a P force down, and let's say we're just going to chop this little section out. So we'll do that real fast, and we'll go down with the P. But then you expose this, and you expose a shear force, you know what I mean? And they don't do it that way. I'm just doing it whatever. I'm probably doing it the exact opposite. And let's talk about sign convention. Because they say a positive shear force is, well, it's kind of confusing. Because what? A positive shear force is, I'll have to go back to the book, but I think it's something that makes your object I mean, you just have to choose. Is your object going to go from this to look like that, or is it going to go from this to look like that? I mean, you have to choose, you know what I mean? And now, is your object, when it goes like this, is that going to be positive, or when it goes like this, you know what I mean, is that going to be negative? So, for this video, I mean, it's just like, who cares? Like, literally, who cares about the sign convention? It wouldn't matter anyway. The fundamentals of what we're trying to explain are the only thing that we're interested in. You know what I mean? We're going to get the moments in the right direction based on that convention. Okay, so here, when we chop this out, that's why we get this 160 force down, and they would say that this is like 160 moment, and then they would say, hell yeah, you're going to get a shear force, and then a bending moment. Probably this way, maybe. I don't know. But let's do it. Let's do it over here, because so we have the forces in the y's balance. So now this is going to cause. Remember how these 160 was working over the entire length? So that was a hella moment. Now we have the same 160s, but only working over half. So now this moment is going to be hella divided by 2. And it's going to be a negative in the negative direction. This one's hella in the positive direction. So how would we balance this? Well, we have hella positive minus half of hella. So now we need another minus half of hella, and that'll balance it. So that's going to be a moment in this direction. So now we'll have a moment in this direction. That will be that hella big one divided by 2. Okay, so sweet. So now we kind of know. And then, but now what the hell does this even mean? You know what I mean? At the end of the day, we need some sort of idea of what's going on. So we are going to just, we're going to take this, we'll probably make it longer, and we're going to apply a torque, you know what I mean? And I'm going to pause the video and get out my rulers, because if I put a pure, a pure moment, we're going to put a pure torque on these, you know what I mean? Let's say we welded bolt heads to this, and then got out our crescent wrenches, and then just started wrenching up, and then wrenching this way, you know what I mean? Just wrenching up. This whole thing is going to bend. And these molecules are going to get longer, these molecules are going to get shorter. So let's show that by spring. So hell yeah, this spring is going to get real tight, and this spring is going to get real long. And it used to be just kind of normal, you know what I mean? But now it looks like this. So if you think of things as a spring, that's probably take-home point number 2. Do the chop it out of outer space. You can't go wrong there. You know what I mean? Figuring that it's not rotating or going up and down. And then the second thing is, hell yeah, if you have this crunching moment, hell yeah. So you're gonna have a tight spring here and then a loose spring here. And what's that's gonna look like? That's gonna look like an arc like this way. You know what I mean? So now our object's gonna be like that. And if we go back to our picture, is that what's going to happen? Hell yeah. You know what I mean? We have a cantilever here, and then we roll down on that, and that's what we got. Okay, so this video is going to be a couple parts. You know what I mean? I make long videos. So that was going to be the intro, and now we're going to pull out some rulers and show that, yeah, the molecules get longer, and we're going to talk about that, how it related to just the basics of material mechanics. Basics of material mechanics says, hey, if you have like a 1 meter bar, you can only stretch it out of steel. You can only stretch it 2 millimeters. And if you do stretch it 2 millimeters, it's toast. You know what I mean? Well, it'll start to plastically stretch, and we don't want that. We always want to keep it within that elastic or springy range. So we don't want to, cause permanent deformations or put a load on it that's just going to rip it in two. Okay, and then we're going to show how that's the case with the bending. I can just talk about it right now. Let's say this was a 1 meter long bar, and now we just stretch this. Well, because it's a curve, and with three-dimensional objects, down the middle, this distance is still 1 meter, right down the middle. It's kind of fascinating. But this outside is stretched out, and this inside is compressed. So with that 1 meter steel, sure, you can stretch it 2 millimeters, and you can also compress it by 2 millimeters. But at that point, that's when kind of the bad things happen. So the same thing with here. The limit on this curve is just by geometry when this is now 1002 millimeters, because this center line, you know, the original length is still 1000 millimeters. And then right here, this would be 998 millimeters. So you could actually take an object. You know, you could do this out of foam. You could take a one meter like foam toy and then start bending it until it changes by you know, visibly by 2 millimeters is hard to measure. But anyway, so that's our tolerance for steel, and whatever moment is going to cause that is the maximum moment. So that's the next thing. What we're going to do is we're going to take, you know, the steel that I would buy at the steel yard and see how long I can make something just welded to a cantilever. So I'd weld all that, and then body weight on it, and how long can this be? So that's the question that we're going to answer. All right, hell yeah. So we have the ruler, and you know what I mean? This is what every material mechanics professor brings out. And so you can't really bend a ruler like in a smiley face this way, you know what I mean? And we'll go over that reason why. You can bend it this way, because again, what we're saying is that, let's say this ruler is exactly 12 inches long. The center line, molecule for molecule, in this ruler does not change length when you do this. It's kind of fascinating. But the top molecules stretch out, and then the bottom molecules kind of crunch up. So if you, but like honestly, if you do stretch this, and then you actually measure, I don't know how the hell you'd measure, like with a string from, you know, one side to the other going here, you would get a slightly longer length than 12 inches. But with steel, you know what I mean, it'd be 12 times that 0.002, 0.2% of change in length. And so you would have, you would change this by 0.024. We're going to multiply that by 25.4 to get it to millimeters. Whoa. I multiplied by 254, divide by 10. So this thing will change length on the top. So this one's kind of buggered up. I don't mind, you know what I mean? So if I permanently, you know, like change its shape, that means that I have stretched it like 0.6, like a half a millimeter. So at that point, when this top thing stretches a half a millimeter, that's when all the molecules got overstretched and won't go back to their original shape. Okay, but for our purposes, for what we're going to be doing is there's two different. I actually never realized there was two different things. I always thought that if you had a bridge and then you put a weight in the middle, that would be pretty much pure bending. But it's not quite. There's subtle differences, and we're going to go over that with the shear and moment diagrams. That was one of the comments. You're like, hey, can you go over that or do some problems? And I had to kind of relearn it. But anyway, so here's pure bending. You know what I mean? I'm just torquing the ends, and I'm just putting a pure bending moment in both of these. And then so when we go to a point right, so then here is just that classic bridge, you know what I mean, where you just have, hey, I'm pretending like my fingers are the supports, and then whatever, it's like an upside down bridge, but then someone's standing on it and making it bend downward. But there is a difference in the shape of this compared to just pure bending. So we're going to go to pure bending, stick it right there, and then I'm going to kind of release, and you see how that relaxes. So the pure bending is a constant curve, and so I can just even explain this when I do pure bending. It is a constant radius. You know what I mean? There's no change in rate. There's no like, whoa, it's like big radius over there, but not too much radius over here. Okay, but when I go like this, pure bending, put it on that, and then put my fingers down and then relax it. It's subtle, but there it is. So these flatten out. So like right here at these ends, there is no curve. And if there is no curve, there is no bending moment. You know what I mean? All the bending moments right there. The max curve is right there. So that's where we get max bending moment. Same thing with our cantilever. When we do our cantilever and we're stuck out like this, when we push down, see how this is just flat as? But this starts to curve. You know what I mean? So if I did pure bending and then went up to a shape, well, obviously it's a constant curve. It's just kind of like a quarter circle. But in the classic welded cantilever, this thing's welded. All the moments over here, but when we go down to push down right here, see how it's just a flat line? You know what I mean? So that was the take-home point when I revisited this stuff. So let's get back to some of the analytics. All right, so first things first is we gotta know the sign conventions. So so here's a positive shear. What I like to think about is, hell, if I have a bridge, you know what I mean, that's kind of supported, and I was trying to look for a YouTube video. I swear, you know what I mean, like a big old truck goes across like a wooden, you know, plank bridge, and I swear it just like shears the wood. You know what I mean? There's enough nails in it, but the wood isn't strong enough that this thing, you know what I mean, it just falls out of the sky. And so that's shear. And when we do that, you know what I mean, if we kind of take a peek at what's going on right there, well, we would have, you know, it's kind of supported, but then we have the Jeep on it. This side goes lower. And then so the molecules that are shearing look like that. You know what I mean? So this is going to be positive shear. Car drives from the left to the right over a bridge, and we want to identify that molecule. But I guess at the same time, if it, you know what I mean? Maybe that makes more sense if a car drives onto a cantilever and then all of a sudden it just drops out. Because over here it's going to be the opposite, and that's going to be the negative shear. Now when it drives across, yeah, it's going to smiley face, and we're going to call that positive moment, and we already went over that negative moment. Okay, so but I think the big mystery is the free body or the moment diagrams. So I'm just going to make sure I don't go over this, but yeah, so we basically have a, you know, like, why does it look like this? And who cares, right? So anyway, and I'm going to put the load right in the middle. You know what I mean? So we have a bridge. We're going to put the load right in the middle, call it P. Well, guess what? We're going to chop it out of outer space. That's kind of the first thing you do. And then wouldn't there have to be a P divided by 2 there, and you know, half the load here, half the load there, and we still have that P there. Cool. And these are pin connections and a roller, so you know there is no forces sideways. All right, so and then this is balanced. There's no other moment. So we did chop it away from these pins, but by definition, these are pins. They wouldn't be able to carry moment anyway. So yeah, they're little you know, like skateboard bearings. You know what I mean? So that's kind of how it's hooked in. You know what I mean? Sometimes the triangle doesn't give it justice, but hell yeah, it's a pin. It's a pin connection. And yeah, you can't, it's not, there's nothing welded right here. It's just free to rotate. Okay, but now we can start cutting this thing up. I'm going to give it some dimension. So we're going to, so now we just know what's going on over here and over there. You know what I mean? The triangles are gone, so now we can just keep cutting. So I'm just going to cut right here. That's the first thing they do. And so again, this thing is just free floating in outer space. We know that there's a P divided by 2. And we opened up, you know, the inside of this. So that's the other thing is like, I don't know, maybe it's kind of hard to make sense, I guess. But like, yeah, if you have a cylinder with 2 loads on it, I mean, if you can't do something simple, it's just like, yeah, it's not setting in. And then we're going to chop this out and then just take half of it. Well, it's going to be the same. You're going to have the same load. But I guess what I'm getting at is like you exposed a face. Anytime that you cut a section, you're always exposing a face. It's very important in material mechanics. And especially how you cut this. Because if you cut it kind of perpendicular like you would, well, yeah, the face is the same direction. But the second, and we're not going to go too much into this, the second you cut it like at a 45-degree angle, and you had a P here, well, guess what? This can only take the normal force, you know, the molecules, because you have a disk of molecules, you know, resting on another disk of molecules. And so because they're at 45s, if you're going to tension them just like normal, that's why we call it normal. Yeah, those molecules are now going to be stretched this way. And we can envision that that's normal. I mean, this is just like, no one explains it like this. But then you also have like a shear force, as well. When you expose a force well, anytime that you cut it, even if you just cut it normal, like a perpendicular, yeah, you still have this P here and this P here. But guess what? They're balanced, and then the shear force is just 0. But in this case, so you have like, hey, only this component in this direction of the normal force is supporting P. So you must have some other component of this shear. So now you must have a normal component and a shear component. You know what I mean? So that's how that works. But for these moment diagrams, hell, that was a little bit over complex, but like I said, it's the reason why you opened up a face. Well, you're going to have a shear, and you might have a normal force, and you might have a moment. You know what I mean? And in this case, they don't even realize that they're cutting it and then saying all the things that you could have. But we just know the normal force is 0 because there is no axial force. And so now we're just dealing with the shear in the moment. And now let's talk about that for real. So we cut it out. We know that there's a P divided by 2 up here. All right, and that's all we know, you know what I mean? Because we cut it on this side of the load. So that's what the textbook says. Like, hey, cut it on this side, then cut it on that side, and then see what you know about it. But, textbooks aren't very good at kind of putting it into a lot of words, and like I do. Anyway, so all we know is that P over 2, but again, if this is just floating in outer space, we can't just have it would be traveling that direction. We can't have that. And the only place that we can have that force is on the face that we just cut open. And so we're going to have a P over 2 downward, and guess what? That's our V. And do we need to go back to our sign convention? Maybe not. Let's use it. The car drives over the track on this way. And then, I have no idea. I don't think this is a good example. It kind of was. But yeah, if it's downward, yep. So anyway, this is a positive shear. And, yeah, positive shear is going to need a positive moment. I don't know, you know what I mean? But it's just like you don't have... Alright, sorry about that. My camera died, but we're back at it. And, you know what I mean? I'm not worried about the sign convention because Newton laws apply. You know what I mean? So, hey, we have this couple that's going that way. We need a moment that's going that way to balance. And so that's what we have in this diagram. And, so cool. And, like, what's the size of this moment? You know what I mean? Because we're going to say, hey, we cut this thing just right up to this load. You know what I mean? The load isn't involved, but we cut it right up to it. Well, we're going to have length divided by 2. So this moment is going to be P divided by 2 times length divided by 2. That's going to be because that's the moment this way, and so we need to counter it with the moment that way. So we already know, the size of that moment. Cool. So now we can do that thing of like cutting into 2. I think this is a really good thing to do. So we're going to cut half of it out of outer space. And now we just have that. Now we have P divided by 2. I apologize. That's a dumb way to... That's the opposite way that I wanted to go. No, we could. That's going to make the most sense. Not to overcomplicate things. Because you could cut that side out too. We'll do that in a second. So over here we got P divided by 2. And then so we must have a P divided by 2 so it doesn't float away. And then that causes a moment. But see how this moment's a lot smaller. This is L over 4. So now we have a negative moment. And so we need to counter it with this positive. I don't know, we have a negative couple, a negative torque, you know what I mean? Also a negative moment. We got to counter it with a positive moment. And that moment's going to be, well, the force, P divided by 2, but L divided by 4. So this moment we'll say this moment's big and this moment's half. You know what I mean? So what this says is at this point, this moment's half. You know what I mean? And then so let's go all the way to the very edge. You know what I mean? Just to where we hardly cut out anything on this left side. Still out of outer space, we still have that p divided by 2 up, and then we must have a p divided by 2 down. But this distance here is so negligible that the moment, it really doesn't create a moment where we could almost say, you know, if this is so tiny, then the moment is basically, or the couple that this is producing is a -0, and then so we just have to couple it with a positive 0. But yeah, so the moment here would just be 0. And then whoa, it's like, whoa, so at P you had a max, and then halfway you had halfway, and then at 0 you had a 0. So this is such a linear relationship. So if I wanted to know the moment at any point between here and here, I would find that max point, which would be p divided by 2, L divided by 2, and then and I would just go down to 0. So this is my moment, and this would be L divided by 2. And now let's assess the other side. You know what I mean? So I think assessing the moment first was a little bit easier to visualize. Oh, but guess what? What was the shear force? Well, the shear force was always just in the same direction. It was down. It was, you know, that's why I never liked shear diagrams. I think this is the reason, because you have to go to a convention. You have to say you opened up a face, and this is your shear. You know, always equal to V. The face that you opened up is the shear that you're observing in that plane. Just like, hey, if we have a normal force here, well, if we cut it at an angle, or it doesn't even matter if we cut it anywhere, we're going to have a normal force perpendicular to the plane, and then a shear force. And, yep. So, but this is where the sign convention comes in. Even though this was always downward, this is a positive shear. And so, I don't know how you're going to get used to that. I don't think I ever did. But that's why over here, you know, you still have, and for this case, it's a little different, but this would just be P divided by 2. So you have that positive shear all the way up to this point. So now let's grab a new sheet of paper and figure it out on the other side. All right, so the initial conditions, the first time we chop it out, we're going to have P in the middle, P divided by 2 on each of the ends. Okay, now we are going to chop it out. And I guess, is there two ways to do this? I mean, because they were saying, hey, just keep chopping it out from this side. So we'll do that, and then we'll chop it out from the other side and kind of see what we get. And we're just going to chop it out with the so now when we chop that out, like P is like right here. We might have just a touch extra. And this is P divided by 2. But now we're still unbalanced. Well, the first thing that came to my mind is like, oh, aren't we balanced now? It's like, no. We have hella and then just half going up, you know, on this point. So now we need what do we need? We need more going up, you know what I mean? So now we have a P divided by 2. This is our V, but with sign convention, this is going to be the negative direction. And then, yeah, now we're balanced. So now we have that going up, and yeah. Now, how would we take moments? You know what I mean? This is where I use the other thing of like, well, could you pin this in outer space? Like, if you can pin it anywhere. So like finding the moments about any point should be 0. So because we go back to our original picture, hey, eyes on it, it is not moving. It's not traveling across the universe at any x, y, and z direction. And what else is it not doing? Oh, yeah, it's not rotating. Sorry, yeah. It's not rotating in a circle. You know what I mean? Okay, so visually we know that that's F equals ma. This sets us up for, hey, the sum of the forces in the x, y, and z direction all have to be balanced, and then no net torques. for the life of me, I need to go back to the textbook and be like, what's the foundational principle of no net torque? But I think I explain it very visually. It's just like, yeah, you can't have a three-dimensional object and forces that are balanced in the y direction, but that are at a distance to each other. That thing's just going to start spinning if it's in outer space. Okay, so this has been really helpful. So this next tip has been really helpful for me going forward with free body diagrams, because what it says is like, hey, you can remove. We already removed all the supports, and we identified the forces. So we still have to take the mass and have the known forces on it. But once we do that, we can, like, this thing is just floating in outer space. We can take a thumbtack and tack it to outer space, and guess what? It's not rotating around that point. And if we thumbtack it over here, it's not rotating around that point. So basically, anywhere where we thumbtack it, it can't be rotating. So, and I think this is a really good, helpful analogy for me, and it works. I'm going to do a thumbtack right here. But this is where you get to the core principles. Let's say this is point A. I'm going to say the moments about A are 0. Well, these forces don't create any moments about A. And if we go back to the thumbtack idea, it's like, hell yeah, now you have like an actual rigid thing like tacked in there. Things can spin around this, but the forces that are pushing against the thumbtacks, you know what I mean, will not help like open this door or make this thing spin around. But this will. Holy hell, this will. You know what I mean? And now the distance is L divided by 2. So now we have a moment or a torque that's this distance. So this is causing a downward P over 2, L divided by 2. So we need to balance it with a positive, a positive moment. And yeah, this is where shear gets tricky. I think. I mean, because moments is easy. Hey, look at it. Well, oh no, this is interesting. If the moment's on that side, it's... Oh, no. Yeah, that's weird. If the moment's on that opened face, it's still part of a positive moment. I don't know how I'm going to get used to that. But anyway. All right, well, let's go back. But I don't think you need to. I mean, the print... Like, once you figure out what size it is and what direction it is, that's it. I mean, whether you call it negative or positive, I don't know. Obviously, it's going to be useful to answer some of the problems. And but I just want to know the fundamentals. And like I said, thanks for joining me. This is what it looks like to revisit when you already went through it. And you know what I mean? You're just like, nah, it didn't really stick the first time. Okay, so we did that time. Okay, so we found our moment. So our moment is going to be a positive P divided by 2, L divided by 2. Right at that point. Hell yeah. And now we can even go farther. So now we're going to go halfway. We're going to do all that and go a little bit farther and go halfway. So we're not all the way to here. Our load is going to be P. We have P divided by 2. And now we... Oh yeah. So, you know, obviously we need to figure out what we have. We're going to have a shear force. And if we have to be balanced, so yeah, we're going to have P divided by 2 up. That's going to be our shear. It's on, you know, by convention, it's a negative by convention. And then let's see what we have for moments. So where do we want to thumbtack? Well, I mean, I assume you have to thumbtack here. If you want to find the moments, I mean, you don't have to. You just need to figure out the moment that's going to balance. So yeah, let's see if I could thumbtack a couple different places. But yeah, if I thumbtack right here, we're going to have this moment of P divided by 2 times 3/4 L. And then this is going to be, so that's going to be a negative moment. And this is going to be a positive, so we're going to go plus, this is going to be P, and then a distance of L divided by 4, and that's going to be, and then plus whatever moment we have, and then that has to be equal to 0. So, I mean, what do these equal? You know what I mean? We have negative 3/4 plus 1/4. So this is going to be P divided by 2, and then we're going to get a half. 1/2 No, I don't think I did that right. Negative p. Oh yeah, because this is. So we want, if we wanted this to be, this is 2p divided by 2. So this, if we brought the 2 inside here, we'd have 2 divided by 4. You know what I mean? So now we have negative 3/4 plus 2/4, which leaves us with that negative quarter. So we still have negative p over 2, but 1/4 L. And that is our moment. So now we have to add that same thing. Moment is going to be equal to, the positive verse. So if this is negative, we'd have to have positive, whatever that is. And now we have a positive moment to balance that. And again, just visually, we have, well, I don't know if this one's a little bit trickier to visualize. But yeah, we have half over a huge distance. But, it's... yeah, we just did it. Yeah, this one you needed a little bit of math. My brain can't handle it. But yeah, now we have a moment that's going to be p divided by 2 and is quarter L. Okay, now, and you'll see a pattern. So this moment is the biggest half, and then we're going to take it all the way to that point. We're gonna cut it out of outer space. But like I said, let's see if the thumbtack method works. Because I'm gonna take the moments from here. So now I'm going to say, hey, if I tack this into outer space right there, we have L divided by 2. So we have P divided by 2, L divided by 2. That's going to be a negative moment. And then we have this one, which is positive. So we have a positive P divided by 2, and this is L divided by 4. Yeah, this gets us there way easier, because this is 2 divided by 4. So negative 2 divided by 4 plus 1 divided by 4 is that negative p divided by 2, 1 divided by 4L. Plus something, it has to be, and then we have no net torques, you know what I mean? So that's where we get that. So you could thumbtack, thumbtacking this anywhere into outer space makes a lot of sense. And it goes back to, and this is the take-home point that a lot of professors won't say, is just like, hey, we visibly, or won't say enough, we visibly do not see this traveling in outer space that way, you know what I mean, with a velocity and especially a change in velocity, you know what I mean, or we don't see it spinning at a slow rate and constantly getting faster and faster, because that's what a force would do. It would cause angular acceleration. Any force that would be in one direction would cause not only a velocity from 0 to some velocity, but a continuous change in velocity, until it probably reached the speed of light or something. All right, so but that's what we observed, that hell, no velocity in any directions and no rotation. Got it. And so now we're going to take that final free body diagram. We're going to chisel this thing. We're going to cut it out of outer space right up to the very end there, where this force still doesn't, apply. So we're going to do that. So here we go. The full length. We have P divided by 2. Now we didn't cut it out to this part, so we don't have a P divided by 2 here. But we have an open face, you know what I mean? We went to the last molecule, you know what I mean? So here's the surface of molecules, and then this is the surface of molecules. And then the load of P divided by 2 in our original was on these, but then we cut it out of that. So now we opened up a face, you know what I mean? Because we could have opened up a face at a 45 and got, different numbers for things. But anyway, so we opened it up at a perpendicular degree angle, so now we need to balance this. Because we know it's not traveling. This is the bigger one, but we know it's not traveling this way. So we do a P divided by 2, it's balanced. And just visually it's balanced, you know what I mean? If I did the thumbtack right here, negative and positive, so cool. Just by observation, moment is 0. And so that's where we get the moment graph. It's peaked right at this point, and then it's 0 on this side. And then the other thing, with sign convention of shear, hey, we have an upward P divided by 2 over here. So this is V, but it's in the positive. So, whoa, and I apologize. You know what I mean? I probably said one thing and meant another. But obviously, no, we got it wrong on this one. So yeah, by convention, if we have an upward force over here, or what? What up? No, upward. Upward is negative. No, we were right. That's why sign conventions are just hell. You know what I mean? I see something that's upward, and I just made an association that's positive. No. It's negative by convention right here. It's on this right side, and it's upward. All right, hell yeah. And, you know what I mean? And did it change? No. It was always, by convention a negative shear, and it was always P divided by 2. So when we go to what this looks like, heck yeah. And let's see if this comes out in the wash, because we were saying A and B. We were going to say A is equal to B and is equal to L divided by 2. Yep, L divided by 2. So I feel like my moment's going to be messed up. Well, is my moment right? It's pounds times length. You know what I mean? Inches, pound feet. That's a moment. Over here, moment is pound. Oh, so they have two variables here. Yeah, A and B. Oh, I get it now. Yep. Because let's just do this real fast. They have PAB divided by L. I'm saying A and B is equal to L over 2. Well, we're going to have two of those. So we're going to have P, and then we have the A is L divided by 2. L divided by 2 is the B, and then we have 1 over L. So we're left with 1 L on top, and we got P divided by 4 on the bottom. If we go back to what we found for our max torque, it was P divided by 2, L divided by 2, which is PL divided by 4. And so that's what, I apologize. I forgot the L right here. But yeah, PL divided by 4. So there you go. So we found that yes, and by that diagram, we're not doing pure moments. We're fixing 2 points. These are flat. I can't do the diagram anymore, but we did that. And there is no moments on the ends. And so that kind of shows it visually. But if you do have this, if you go to something and then put a moment on it like that, hell, this thing is just going to have just be solid, just like that, all the way across. And then our shear forces, by convention, we found that they were positive, but once we got to here, they switched to negative. You know what I mean? I still, once we do some problems, yeah, maybe I can find some other tricks of the trade to have this settle in. But, to just jump back into it, hell yeah, Newton all the way. You know what I mean? That's why any physicist that's really not into material mechanics and this type of engineering, you know what I mean? You could explain it in a way that they're just like, oh, I get it. You know what I mean? But it's all like, hell yeah, you have a mass, and then you're observing that there's no acceleration. And no rotation. You know what I mean? But then your forces have to balance for the no traveling in one direction, and then your torques have to balance for the no rotation part. All right, so we did it there. Hell yeah, I'm going to take a little break and probably get back to the cantilevered problem, because cool, we found moment. Who cares? You know what I mean? Like, who the hell cares? You found a number for moment. What the hell does that even mean? And like I said, it's just like, well, when we did this, you know what I mean? I'm more fascinated in the change in length. Because if we did this just by geometry, we could figure out the curvature, and then we could figure out if this thing's totally screwed, or if it goes back and it's going to be all in the same shape. So now we need to relate how moment relate. And I'm not even going to do a very good job of it, because I'm going to do an example with my welded steel that doesn't require any moment of inertia, that will be required. But I'm going to show you that, hell no, a moment is just a couple, and so I guess we have time to go over right now. So when we it's probably bad, kind of too curved or whatever, but so here's our chunk of steel, and we're gonna say we're gonna put a person on it this way, and so it's going to curve, like that, and the top's gonna get all crunched up like a spring, and the bottom's going to get all lengthened, and we know that a moment's going to be applied this way and this way, and I think I already went over that hell yeah, it's going to be, if the moment's like this, then yeah, this top's going to get crunched up, tight spring, and then this bottom's going to lengthen spring. But the only thing that's actually going to prevent it from like getting shrunk up here is this area. You know what I mean? Like, let's say, forget about the sides for now, and you really can. They hardly do anything. But we're going to say, hey, this area is the only thing that can take that force, and this is the only area that can take the force to lengthen. Maybe that was not a very good way to say that. But again, if we have the two moments, oh yeah. So this will be good, and maybe get some more paper. But we're going to have we can replace this moment with a couple. So even though I'm drawing over here, so we can say, hey, we got a force this way and a force this way. You know what I mean? And so now that's a couple. And here's our distance, and for our problem it's going to be 2 inches. So we took this moment, so now we're going to say, hey, this moment is equal to this couple, and we know the definition of a couple is just force, pick one of the forces times the distance. And let's slow down here, because none of the professors do. If we have 2 inches, that means this is 1 inch and this is 1 inch. And we're saying that we have and I'm just going to go back to P, and then we have a force P right here. So let's thumbtack it right here. Well, hell yeah, this force P is going to produce a positive moment that's going to be P times 1. And then this force is going to be P times 1. So we're going to go P times 1. Well, guess what? At the end of the day, that's just 2P, and that's exactly what we get. We get 2 inches times P. That's this moment. Or you can just take one of the forces, P, times this total distance. So P times 2 inches. Gives you that same thing, just a lot faster. But visually, and I guess we could do the thumbtack method. It's like, hey, we're going to analyze that, thumbtack it right there. And this thing is in outer space but not moving, and so it must. Oh well, no. That's maybe a dumb way, but I don't know if that's a true statement or not. But anyway, if you want to find the torque of a couple, do that. Just take one of the forces and multiply by the distance. So when we do that, we can use our equation for moments. I mean, we did the free body diagram to find the max moment, so we can do that. And in here, the max moment was real easy. It was just PL divided by 4 is this one. Cool. So I can say I'm 160 pounds, and I was gonna try to do 240. Yeah, 240 inches, and divide by 4. So hell yeah, we can do our moment. 160 times 240. I was thinking I just needed and divide by 4. So our moment, if I bought a 20-foot, steel tube, which I like to do, 2 inch by 2 inch, and we're gonna have 9,600 pound inches is our moment. So we come over here. Well, that moment is only resisted by the force up against those 2 points. So that moment of 9,660, hopefully this works out, it should, is going to be equal to the force times 2. And so now we can figure out what... I'm going to pause. I don't even think that was right. No, we're good. We're good. But it's just interesting when you get lower numbers than you're thinking. But so anyway, so we can find the force. It's just this divided by 2. It's 480 pounds, and I just didn't think that was, because steel's real strong. But hell no, our area isn't very big. So now we go back to material mechanics, because this is just, it feels like you're doing theory. But at the end of the day, hell yeah, first equation, material mechanics, strength is force over area. That's all we need to know for this one. And now we need to find, and we know like the yield or breaking strength of steel, or when it moves. Let's say it's 58,000 pounds per inch squared. And so now we just multiply by the area to get the force that we can actually have. Alright, so what this is saying is that, what this equation basically says is we rearrange for force, and we can say sigma YA, so that this is the max force we can put on that area, and that's going to be 58,000 times this area, and we have an area of 2 inches by the thickness, so we have 2 inches by the thickness of 0.083. You know what I mean? That's what we bought at the steel yard. So we got 2 times 0.083. That's going to be the area, 0.166, and now we're going to multiply it by 58,000. And, multiply by 0.166. And we can have a force of 9,628 pounds. Cool. So, we only have a force of 4,800 pounds. Oh, no duh, no duh. Okay, so yeah, this is fascinating. And no, this is cool because the reason why I was getting sweaty was because doing this with a cantilever, because we'll do it with the cantilever and call it a video. Because if I get a 20-foot length of this stuff and then weld it, and I would love to do this, you know, just go up to something and weld it to it, then stand on this with 160 pounds, no, this is too much. It's going to put too much moment into that. So that's the next thing we're going to do. We're going to show that, but for this problem, we're just going to be like check on reality. Like, hey, this can take 9,628. I can only buy 20-foot lengths of this, sometimes 24. But no, I'm good to use it as a bridge because I've kind of worked at this cabin, and I'm just like, hell, I'll just use one of these as a quick bridge, and you will not yield it. You know what I mean? You can walk across it as many times as you want, and we just proved that from the moment, the couple, and then just the force right there. Okay, so hell yeah. So now I'm going to try to write a little bit cleaner. We're going to do the same thing with the cantilever, do the free body diagrams, and then go back to finding that max moment. And it's real simple. Just visually, you'd be like, well, didn't we just do it? It's fixed on this end. And when we go down, and I'll do it with the newer ruler. And when we go down like this, look, this is totally flat. There's no moment here. All the moment, the highest curve is up there. So when we do the cantilever, we're gonna all the moment's gonna be right at that point. And that's where those molecules are going to get stressed out. That's where you're going to put a hugely high force into just that surface area. You're going to get a huge couple. So yeah, we're going to identify a big couple, and we're going to equal that couple to the force. How do we do it? Oh yeah, we're going to get an equation for the moment that's going to be related to my weight times the length of the darn thing. So this moment's going to be huge. So this number is going to be hella huge, and it's going to be way bigger than, and then we're going to be able to find the force generated in that area, and this number is going to be skyrocketed compared to this. And the take-home point is we have to chop it down to 10 feet. 10 feet with a cantilever. You could walk out 10 feet, but if it was longer, you still could. Like, I'm just saying, it's not going to go back. Every molecule is not going to go back to the same shape. Because honestly, steel can bend so much. And as long as it doesn't tear, as long as something kind of helps it bend, and it doesn't just like brittly tear and break at like one highly stressed point. I mean, the second this does bend at any angle, I mean, the geometry is going to be way more conducive to take more weight. Compared to a cantilever that sticks straight out. Alright, hell yeah. So, catch you on the flip side. Alright, hell yeah. I keep thinking I need to go back to a book or something, like I can't solve this or whatever. But we're going to do the same thing. We're going to take the cantilever from this side. And let's analyze. So we have the load down, and we're going to chop it out of outer space. So we still have this load down. What do we have over here? Well, we opened up a face, so we're going to have, this is going to be our shear, and let's see what the sign convention is. It's up on this side, so it's going to be a positive, so V, and it's going to be a positive shear. Cool. And now, what the hell did we just create? We created a huge moment. So if this is in outer space, it's going to start spinning. So we need to create, we need a moment this way. And by convention, even though that's a positive moment for all intensive purposes, it's over here, so it's going to be a moment, but it's going to be negative. You know what I mean? For our diagram, it's going to be negative. And it's basically because positive moments on positive moments. So if you got a moment this way and then a moment this way, so a positive and then a negative. Well, I mean, which is also called you get a smiley face. So we're basically saying anything that makes something smiley face, that's going to be a positive moment. So it's going to be what we consider definitely a positive or counterclockwise moment, but also coupled with a right-hand rule thumbs down moment. All right, so we're getting more used to that. Okay, and the moment, and this is L, so the couple involved is PL, so we're going to get a moment of PL, and it's going to be, by convention, negative. Yeah, I hate that. I mean, I don't. Let's forget about convention right now. So we have a torque that what we call, for all intents and purposes, negative. So this is going to be a positive P divided by L. But then at the end we'll make it negative. So there's two things going on there. You still have to get the direction right. And then by convention you got to figure it out. So let's not worry about the sign convention for the time being. Okay, now we are going to and you could chop out like any side now. Like let's do both just so we get some more practice. So we're going to do the harder one. We're going to chop out half of it this way. So when we do that, we have everything over here. We have a P up, and then we have that moment PL in this direction. Cool. So if we do our pen right here, we have a PL this way. So that's a positive, so we need to balance it with a moment this way. And the moment this way will be uh-oh. Oh, my bad. We chopped it out first. First thing you want to do is make sure it's not traveling in outer space that way or this way or downwards. So we identified that we have a P there, so we must have a P here on this open face. Cool. So now this P creates a torque, a negative P 1/2 PL. You know what I mean? And then this is a, so that created a downward PL. This is a positive, and that created a positive, 2PL divided by 2. So now we have negative 1/2 plus 2/2. So we're going to have, so the total moment here is going to be positive 1/2 PL. Cool. If we have a positive 1/2 PL, we need to balance it with a thumbs down 1/2 PL. Cool. So that's what we have here. We have the moment here, PL, and then we have half over here. Okay. So yeah, like and then don't lose your mind. Again, we were saying the max moment's going to be here, and we've already said it's P over L. Halfway, it's 1/2 P over L. So just by linear relationship, what do you think it's going to be just right over here? And we'll get to that, but let's chop it this way now. So we're going to chop it this direction, just to show you we can chop it both sides. So we have obviously this visual P down. We have to have a P up so the thing doesn't just travel across the page. It is spinning now because we have this torque, and it's doing so with a torque of P L 1/2 PL. So it's P times L over 2. And that's going to be a downward torque, so we must have to balance it with a 1/2 PL, to get a no net torque. And so that's going to be our moment. We cut this side out, and so we're going to. All right, hell yeah, we're back. So my camera totally overheated, had to take about a 15-minute break, and so what we've been doing is we've been cutting out the other side. We finally found, what makes the moment. You know what I mean? So there you go. So we have a moment of 1/2 PL, And it's in that direction, you know, it's in that direction is positive. And let's go back to our sign convention. Hey, that would be a, that would be a positive moment. Oh, damn it. Nope. Yeah, well, what am I doing? What am I doing? Okay, so we just, yeah, it's been a while. So I just chopped this out. All we knew about this is we had a force up there. So we did that, and then this is the face that we opened up. And then so we have to neutralize it with that P. Perfect. So then whatever moment's going to be over here. And so this is creating a negative, so we need a positive. So this is our positive direction, you know what I mean, couple. And that's going to be equal. Moment is equal to be 1/2 PL. Then by sign convention, you know what I mean, we look to be like, okay, it's downward. Oh, so that is going to be a negative sign. When we do our shear graphs, you know what I mean, when we do this, then our moment would be a negative moment. All right, and then same up here. We have the same moment over there. P over L is going to be our max moment. It's going to be negative. So, I mean, could we just kind of assume what our moment graph is going to look like? It's going to look like that. So you would have a max negative moment. And a positive moment, again, makes a smiley face. Negative moment, well, it's probably going to do that and make a negative. And it does. That's exactly what we see. Cantilever with the weight this way, it's a negative smile. It's frowning. All right, so so we did that, and now the only other part was be like, okay, let's cut this whole thing, but right up to the molecules over there, and so now we have this force P known. We have this moment P divided by L. We found that. But now over here, we don't include this P because we're saying, hey, we have a stack of molecules there, a stack of molecules. This P acts on that stack of molecules. And we cut this out, this whole thing out. And so we don't observe that. Visually, you know, there is no downward force on these molecules. But we come over here and be like, oh, well, yep, there is. Because it's got to be balanced. So we have this P up, P's got to come down. And then we look to see what this moment does, and it's putting a negative PL. And then this, I don't know why I did P divided by L. I apologize, that was a huge mistake. No, the moment is P times L. So we have P times L, and that is, so apologize, should have caught that way long ago. But there you go. So the moment is, I mean, it's basically the couple. It's the force. We've already talked about that. You have two forces, and then the distance in between them. It's just one of the forces times that distance. Cool. So P times L. And then this one, and if this was PL, this moment was half of that, PL divided by 2. So now over here, we know that we have a moment PL. And we know that this couple makes a negative PL, we have a positive PL, and then guess what? We can't add any moment. So this is the face that we cut, so our moment is just 0. So there you go. And that's exactly what we wanted to do. At any point in this, what was our shear? You know what I mean? So we opened up this face, our shear was down, cool. And then we opened up this face, our shear was down. You know, we keep doing that. We could just go right up to, you know, once we already opened it up, we could go right up to that little chunk. And so we have this upward P, and then there must be a downward P. So cool. So our shear graph is very simple. Our shear has never changed. And by convention, over on this right side, it was a positive shear. Oh, am I going to get messed up? Hopefully not. Yeah, I'm not very good at understanding the shear diagrams, but at the end of the day, all we wanted to do was find where the max moment was. We found it. It's PL. So now we know that we have a max moment of PL. But let's take a second and see if we could do our shear diagrams. So we were saying that this force when we opened the darn thing up, we found a shear force of P, and it's a positive. Okay, so and that's going to be all the way up against that molecule. And then even when we get up to the force, it's still going to be P until we get right there. Once we take the sliver that is So our shear is just going to be P, and it's over the entire length, and it's going to be in the positive. And then our moment, oh yeah, this is wild. I don't want to make any mistakes. Yeah, because everyone's confused about the shear and moment diagrams. Alright, holy hell, because, you know what I mean, sign conventions are crazy. So what we found was we definitely knew, if this is our cantilever, that the moment is going to be negative. So we draw our shear diagram. The moment's negative. We know it's got a max of PL, and it's going to go to 0 once we get to the length. The one thing that tripped me up is because now we're going to do the shear equation. This was the moment. Now we're going to do the shear. Well, we knew that was positive the entire way. Hold up. All right, hell yeah, you know what I mean. I read the literature, and we need to take a hard stop. But this is why we do that, you know what I mean. And then in the next 5 minutes, we should be able to find a solution. So let's redo this cantilever problem, like exactly how we want it. But we're going to use that strict sign convention, because what I was basically teaching was perfectly correct for statics and Newton's law, but this sign convention, and when it comes to bending moments and shear diagrams, it is very specific, and it's specific for a reason. So I would like tattoo this, you know what I mean, memento style, because it's hella needed. All right, so we have this P in this length, and now anytime that we make a cut, and we've already said we can make a cut out of, because what they typically do is they're going to be like, well, we already know that force, so might as well just take the cut this way. You know what I mean? We don't know anything going on over here, so well, let's just take it halfway. And so now we can go down here. So we just exposed a face. So that's when we need to go to our chart and be like, whoa. I mean, it's basically this. This is the sign convention. We exposed a left-handed face, and we want the positive direction. You know what I mean? Like, we're just going to assume that we have a positive moment, a positive. There is no difference than doing this. Like when you have like a bar, and you're saying, hey, I have a load here, P, and this is A, and this is point A and B. And you're going to say, hey, I have a AY and an AX. And then I have a BY, you know, because it's a roller. So I have a pin connection and then a roller connection. Well, some problems, I mean, you're just assuming all these. You know what I mean? You could have the, there's plenty of problems where you just assume all the positive directions, because we do our axis. This is Y, this is X, this is the positive Y, positive X. And we're fine with that. But then we reach a point in our lives that we have to figure out bending moments and shear diagrams, and we have to use their convention. So cool. So we have this force down, and we're going to say, hey, we're going to figure out the positive. So we're going to have a positive shear force up, and then a positive moment that direction. And now we just see what we come up with. Again, we don't know these. So right now we just chiseled this out of outer space, and we must have to have a force that balances it. Well, if V is up, so this is where, so if V is up, oh, damn it. I thought this was going to come out in my favor. Well, we'll keep going with it. We'll keep going with it. So yeah, force down. So V is equal to P. So V is equal to P, and it was a positive. So it was a positive moment. It was a positive shear. So let's figure out the moments now. So we have this direction for our moment. So to balance, we need this direction. Yeah, so this is where I'm getting the opposite of this. So if I'm saying, if this was L over 2, I'm saying that my moment due to, V is equal to P, I'm going to say that moment is in this direction. Using static sign convention, this is a negative PL over 2. So it's going to be negative 1/2 PL. And then, so I would need to balance it with a positive 1/2 PL. And so the convention would be this way. So I'm going to say that my moment is going to be negative 1/2 PL. Cool. So now we have that. And then when I get to here, it's going to be the same deal. If I chopped it farther, I'm going to get a moment of negative PL. From this convention, it's going to be negative, but my shear is going to be a positive. I guess I get the same thing. So I don't get it. I still don't get it. I don't get how I get a positive shear of P, but then when I go down here for my moment diagram, I get a negative like negative PL for my moment and 0 right there. I just don't know how the area of this thing equals, how the area under this how do you say that? Yep. Oh, if you, and, But anyway, I'll take another pause. All right, we're gonna take one more stab at this because the book shows that you should do the cantilever the other way. You know what I mean? And then the sign convention works. So, but we'll try it. So we have our P there, and we're gonna chop the hell of the whole thing out. You know what I mean? And we want to know our moments there. So we're just gonna do it all in one go. And when we expose this face over here, we're going to use our sign convention in the positive direction that this is positive V, and then this is positive M. So now, look, these two arrows are going in the same direction. So now we get a negative. So it probably was that. It was like, well, you can't do, like if the sign convention, if you have to take every cantilever and make it this way. So I'm gonna look into that. But I mean, I think at the end of the day, this is the headache of shear and moment diagrams, where I couldn't have done it the other way and just used the sign convention. Like I don't get that. But here now, when we sum the forces in the y direction, where we're gonna have negative P minus V has to equal 0. So now we're gonna get V is equal to negative P. Cool. So this is the positive shear, and this is the positive moment, but guess what? We get a negative value. So now we know that our shear diagram is going to be a negative P. Cool. Now we need to figure out, and we know this is next, so it's going to be up. So obviously we get that couple this direction, positive couple, and it has to be balanced by M being that negative couple. So M is also going to be negative PL. So then we do that. But I mean, that's crazy that I had to just change like, if the cantilever is going this way, the sign convention works. If the cantilever is going the other way, it seemed like total madness. But now this makes sense. So now we have negative PL to 0 here. And if you integrate, because you have to start, you know what I mean, at one of the, you have to start at this end, because if you integrate and you take the area under this, well, the area right here is that area, and then we're going to add just a little bit more. So we But anyway, so that's how you do the integration on that. And I mean, so that was probably a horrible introduction, but it shows you the hiccups of using the sign convention and how to make things work. So now every problem that I'm going to be doing, I'm going to be like just doing examples. I'm just going to do the examples out of the book just to copy them, and then I'm going to manipulate them and see if I can still get the same answers. You know what I mean? Just by like doing the mirror image of the setup. All right, but at the end of the day, we got max force is essentially absolute value of P over L. So if I'm 160 pounds and I bought 240 inches or 20 feet of steel, we would have 160 times 240. So we would generate a moment of 38,400 pound-inches. And again, we have that steel that I like to buy. It's 2 inches by 2. Wall thickness of 0.83. And so when we have this max moment right at that little piece, we're going to take that little 2-inch piece and we're going to say, and it's a downward thing. So again, it looks like that. And if it's downward, our sign convention is a negative. So we're going to have a moment like this and like this. And obviously, this is going to be a bunched up spring. This is going to be this top part's going to lengthen, the bottom part is going to crinkle up. And if we take that over, so this was the moment, we can turn that moment into a couple and say, hey, we got a P going that way and a P going this way, kind of on both these faces. So now, you know what I mean? What's the max compression or tension force, just on that area? That area is 2 inches times 0.083. And we know from our strength is force over area. Strength is 58,000 psi. So we're going to go, the force is strength times area. We're going to do that 58,000. Sorry, I'm getting sloppy. I just wanted to be done with this. Times that area. So we got 2 times 0.083 is that area times that 58,000. So we generate. We can only put a force on that part of 9,628 pounds. So now we go to our couple. We're going to say, hey, this moment has to equal 2 times P. You know what I mean? Or this is now going to say, hey, if I say this is moment max, this is let's say this is the moment required. You know what I mean? Moment required. REQ. What's the P required? So we're going to rearrange and we're going to go P is moment required divided by 2. And we get this. 38,400 divided by 2, which is a pressure of 19,200 pounds. But it can't take that. This is the pressure that we would need. This is the pressure that it can take. So now we have to kind of figure out how to make an equation to see, because this moment is involved with length. So now let's do it. So we're going to basically say the moment generated has to equal 2 times P. And the moment is PL is, two different things here. Different P. So we're going to say this is F. The force required in this. So we're going to change these to F's. I apologize, because initially we were saying, hey, this P is going to be the 160. So yeah, so we're going to say moment is equal to 2F. So now we have a relationship between these. We can solve for F. F is PL divided by 2. That's going to be the 100. No. we want to solve for the length, because holy Toledo. Let's just do this and be done. But yeah, take a breath. So yeah, this moment ain't changing. No, this moment is changing, because if we change the length, this moment will go down. Cool. So that moment is PL. And that moment has to equal the couple that we can tolerably take. And that couple is going to be the F that we found times 2. So 2F. Cool. So the only thing that we don't know is the length that we need to make this. Because so we're going to go length is 2F divided by P. Because F is the force in that little area because of the couple. That 2F is the couple. That's the max moment. So 2F is the max moment that we can take. So that has to equal the moment due to geometry over here. And the only thing that we can change is length. So here we go. So we have 2. And this F, if you want to throw it all together, this F is sigma YA. So we can go 2 sigma YA divided by P. So this is the equation. It says, hey, 2 times 58,000, which would be a good yield stress, pounds per inch squared for steel, times the area, which is going to be 2 inches by 0.083 inches. And then so the inches cancel. And then divide by, where do we get length out of this? Yeah. Oh, we're missing one parameter. All right, I'm gonna seriously take a pause because we need to get this right. All right, now we're good. It was just right under my nose. So you know what I mean. Hey, this is a square tube. We're gonna say, hey, this square tube has a side A of 2 inches, and now our equation. So this 2 was part of the equation. You know what I mean. So now we have length is equal to A. Yield stress area divided by P, which is the pounds that I'm going to go stand on this thing. I'm going to weld it, stand on it, and now we have an equation for length. And so the equation is going to be 2 times 58,000 times our area, which is 2 inches times 0.083. And then we're going to divide that by 160 pounds. So we get a length of 120.35, and thank God I've done this problem before. And so this is in inches divided by 12. And so if we're going to weld, if we're going to go to the steel yard and get this type of steel, weld it horizontally for a cantilever, and go walk out on it and then walk back. And we can go walk on it as many times as we want. But it's going to reach it can only be it can be 10 feet long. You know what I mean? End of the day, 10 feet long. Any longer, it's going to be permanently deformed. And when it does get deformed, like I said, it'll probably increase in strength because the angles are hella better. You know what I mean? And steel can bend quite a bit and not tear. But there's definitely places where steel can just rip like aluminum foil, and it could. I mean, you're taking that to the yield. There's no reason why it just won't keep yielding and then tearing. Second, you get a tear, it might, so you can, when you reach yield stresses, you still could be close to catastrophic failure. But obviously this will probably bend and it'll probably just get hella stronger, and I envision you can just, start cranking on it quite a bit. But no, I mean, because it's a rigid structure too. Like I said, you can get tears to form, and it's not just going to, uniformly bend. Like if you help it, and put rollers everywhere. I mean, you can bend steel as much as you could take this and put it in a machine and bend it, but you're not getting those high moment stresses. Obviously, you're balancing it all out. So a cantilever hella puts moment stresses right there. It really starts to tear that top, crunch the bottom, and you could have a catastrophic failure. But anyway, so that was the problem. Go weld it, and then you could only do 10 feet. So. And this is a very simple way. So like, oh, well, yeah. So let's let's take about 2 minutes to talk about how material mechanics is the properties of you can only put so much tension on some metal or compression on some metal, or watch it change its length. And that's what we did with the rulers. Like that's the top part is stretching out, the bottom part is crunching. The other aspect of material mechanics is just geometry. It's leverage. Because I could take this problem and do this with it. I could do a cantilever, do a hinge down here, and then so if there's a perfect hinge right there, and then this steel is just welded, just that area of steel is welded right there. Well, I think it's kind of the same. It's that really explains what's going on from a leverage perspective. I'm hinging right there. I'm just pulling tension on that cable. So this problem is very simple. So we could do this. Let's say it's that 120 inches and 160 pounds. So my leverage is 160 times 120. Now this, from the pin connection, this has to resist with a force, and this is only 2 inches. So now I'm going to divide this by 2, and I get a force of 9,600. And what can it take? Well, we already did this problem. You know what I mean? And so we have 0.083 times 2 times 58,000 is that 9,600. So sorry, my drawings are a little bit sketchy, but it's more the talking through it. You know what I mean? That's where I can provide value of just like, because I could talk through that same thing again. Let's just draw it a little cleaner. So we have that same thing, but now we're going to weld a skateboard bearing, so it's just a pivot. We're going to cut all the other metal away except this top piece of metal, and then just weld that right to the beam. So essentially we have a rigid structure that's just pulling this piece of metal in tension. And that's 100% what any sort of bending does. You're just putting a leverage arm on it. That's why you can make bridges and stuff, but they're a factor weaker than the strength of the individual components. If you just had forces underneath them. You know what I mean? The fact that you get something really spanned out, hell yeah. You have steel that can take a ton of force axially and in compression, but yeah, the second it's a beam, you're just a factor of 100 less, or even more. I don't know, but yeah. But anyway, so there you go. So there's the cantilever. This distance, so there you go. This PL, this P times L is your leverage, and the only thing that can resist it is this tension in there times that distance. So you basically have PL is equal to tension times distance. This P is normal, 160. Length is really long, and this D is hella small. So when we divide by a hella small number, we get a huge tension. But that's the cool thing. Just a little bit of steel is pretty strong. So, all right. I'm done. That was a pretty decent introduction for me, and that's cool. Like, it's kind of like, yep, I'm not prepared to dive into the shear and moment diagrams with authority, but I can at least tell you, kind of from a perspective of after graduating and then returning, is just like, no, I don't think it was taught in a way to make it stick. And this sign convention stuff, what a hassle, you know what I mean? But that's all right, because at the end of the day, it's just like, well, who cares? Didn't we get if we couldn't draw the drawing right, if we didn't know it was up or down, at the end of the day, we found out the max moment, you know what I mean? And we just knew by observation what it would look like. So, all right, so I'm going to be done, and thanks for joining me, and that's a video. Alright, hell yeah. One more thing before we go. So there's an equation that you can plot like the deflection. So this is going to be our 10-foot steel beam. I'm going to stand on it, and guess what? It's going to dip down 8 inches. That was kind of wild to me. But that's cool because it's still within that linear elastic range. You know, don't quote me on that, but you know, I mean, because we didn't do the equations 100%. But yeah, maybe. And comparatively, if we just spanned this 10-foot you know, thing out, the equation's only for half of it. But if we spanned it out like this and then just put our weight in the middle, it only deflects a half an inch. And that's what kind of what we'd expect. I've used these 20-foot steel 2-inch tubes for bridges. I've already mentioned that at 20 feet, just fine. But at 10 feet, yeah, only a half-inch deflection. But damn, welded as a cantilever, this thing's going to just bend down like a spring, but hopefully it just pops right back up. And I can imagine that now, you know what I mean? But once it bends down to 8 inches, then it's going to hold firm. But this might be the limit on it. Anyway, so hell yeah, that was kind of just cool to show. And sure enough, you know what I mean? If this is our cantilever, hella radius of curvature in there, and then it really slacks out to straight out. And then we were going to compare this. I know it's just half of it, but we were comparing pure bending, where you have the same radius, to if you have fixed supports, and then in the middle, you know what I mean? That is what you get. You get no curvature there because there's no moment. No curvature, no moment, and then hella curvature, your biggest bending moment right where that middle weight is. Okay, so thanks for joining me, and that's a video.